Hi guys, and welcome to today's video. In today's video, we'll go through the different interrupts line priority concept, and we'll see how we can preempt a lower prior interrupt via higher prior interrupt. We'll see how we can program the different NVIC registers to set up the different priorities for each interrupt line separately. And finally, we'll see a demo running on STM32 microcontroller to set up priority for different interrupt lines. From functional point of view, the ARM Cortex-M based microprocessor is adopting what is called the preemptive interrupt handling or management model. Means we can preempt a running task or lower prior interrupt using a higher prior based interrupt. ARM Cortex-M based microprocessor does support two types of exceptions and interrupts. We have the internal exceptions like hard fault, pass fault, SysTick, and so on. And then we have the external interrupt lines. The handling and the configuration of those internet exceptions in terms of priorities is done via some CPU-based registers and some system control block-based registers. However, the handlings and the settings of the different priorities for those external interrupt lines is done through the NVIC registers. Here, within this video, we'll go mostly through the configuration and the settings of the NVIC registers to set up the priorities for our different external interrupt lines separately. So as you can see, guys, this table basically is defining the priorities of different internal exceptions supported by ARM Cortex-M microprocessor. I stated before, there are two types of exception and interrupts. We have the internal exceptions like the faults one and the SysTicks and so on, and then we have the external or system on chip based interrupts. Now the priorities for those interrupts or external interrupts is defined via the NVIC registers. However, the internal exceptions, either they're going to have some fixed priorities, like we see here, for reset, for NMI, for hard fault, and so on, or programmable ones via some system control block registers. However, as stated before, for the system on chip based interrupts or external interrupts, they're going to have priority settings through some NVIC registers. The handling and the settings of the different external interrupts or system on chip interrupts priorities is done via some NVIC registers, and to be more precise, via those interrupt priority registers. We don't have a single register, actually we'll have multiple registers to cover all the supported interrupt lines within our system. Each interrupt line will have a single byte or 8 bits to configure its priority. Hence, we can have the support of up to 255 priority levels. So guys, this is our Keil-MDK project. As you can see, this is a C-based project that has been compiled from an ARM Cortex-M based platform. Our platform is an STM32 microcontroller, and the program has been already compiled and loaded into the STM32 flash memory. Keil-MDK debug session already started. Now our program consists of taking those two interrupt lines, the window watchdog timer and the PVD interrupt lines. Then we'll try to enable both interrupts, and then we'll try to play a little bit with the priorities of each one to see how we can preempt basically the running interrupt. Now, if we don't modify anything on the NVIC side, means both interrupt lines will have the same priority, which is 0. So the interrupt priority registers, the reset value of this registers will be 0. Hence, this one and this one will have the same priority level, which is 0. If this is the case, then the position of those interrupt lines within the vector table will determine the priority of each one. Lower the position, higher the priority. Here the window watchdog timer is occupying position number 0. However, the PVD is occupying the position of the index number 1 within our vector table. So this one, because it's occupying lower position, will have higher priority compared to this one. Hence, if we don't modify the NVIC interrupt priority registers, then both will have the same priority from NVIC side, and therefore will fall back basically to the position number to determine the priority, and this one will have always higher priority compared to this. If we go back to our main, we are first of all generating a window watchdog timer interrupt. Then we jump here, and here we are trying to generate another PVD interrupt, because this one has higher priority compared to this one. Therefore, there is no way that the PVD will be able to preempt the window watchdog timer if both both, let's say, have the same priority level, which is the case because we didn't modify the NVIC interrupt priority register. Now the second case, we'll try to play a little bit with the priority, and we'll try to lower the window watchdog timer priority. This is of course by programming the NVIC interrupt priority registers. Here we can use basically this CMSS based macro to reconfigure the priority of our interrupt line. So the window watchdog timer will have priority number 1, and we'll keep the default priority for our PVD, which is 0. Lower the number, higher the prio. This will have number 0, this will have number 1, so this will have higher prio compared to this one. And this time, the PVD will be able to preempt the window watchdog timer because it has higher prio compared to this window watchdog timer interrupt line. Now let's start. So the project has been already compiled and loaded with the default configuration in terms of priority. So both will have the same priority levels. Now let's set breakpoint here. So we jump into our window watchdog timer. Then we'll try to trigger another PVD interrupt. Theoretically, we should not jump here. And this is the case. So we're not able actually to jump to our PVD because both they are having the same priority in terms of the NVIC interrupt priority registers, but this one has position lower than this one. It means has higher priority, so the PVD cannot preempt the window watchdog timer. Now, if we check the core peripherals, and to be more precise, the NVIC, we can see that we have the interrupt number 16, which is matching basically our window watchdog timer in active state. However, we have the interrupt number 17, which is this PVD, is in pending state. So it was not served because this one has higher priority compared to this one. Hence, the PVD was not able to preempt our window watchdog timer interrupt. Now, let's try to lower the priority of our window watchdog timer by programming higher number within our interrupt priority register. So we'll try to recompile our project. So far so good. Now if we check our NVIC registers and we go down, slightly down, we can see that in terms of priority, our window watchdog interrupt has higher number compared to this one, for instance, which is number 17. Therefore, this one should have lower priority compared to this one because we higher the number. So higher the number, lower the prio. Lower the number, higher the prio. So this is inverted. Therefore, this one will have higher prio, and hence the interrupt line number 1, from external interrupt point of view, will be able to interrupt or to preempt basically this one. 16 and 17, this numbering is compared basically to the starting point of our vector table. So vector table is starting from here. So 16 basically is added on top of those numbers. So this will be 16 and 17. But 0 and 1, this is compared basically to the position in respect to all external interrupts. It means we are starting counting from here. So back to our program. So now we are within our window watchdog timer. Now this one has lower prio compared to this one. If we try to trigger the PVD, here we go. So we're able to preempt basically our window watchdog timer. So as you can see, if we play slightly with those priority bits and numbers, we'll be able to lower or higher the priority of certain interrupts line, which is quite critical basically for our embedded based application.